Hello, everyone. My name is Monica Cintron. I am the marketing manager here at Astrodyne TDI, and I'm joined today by Anil Kurugod. He is our field application engineer here at Astrodyne TDI for the Central region. He's been working at Astrodyne for over 10 years now and is an expert in power solutions and provides a lot of support to a lot of our customers. So we'll go ahead and get started. Just to give a little bit of an overview about Astrodyne. So our company has over 60 years of power industry experience. We develop and manufacture power supplies, EMI filters, and now isolation transformers. And we have over 1,000 employees worldwide. We have two factories in China, one in Malaysia, and we are local here to Hackettstown, New Jersey. And we'll also share a little bit of a confidentiality disclaimer. This is just standard to our industry, but I just wanted to push this over to Anil. Anil, I know that the healthcare industry has been growing in the past couple of years, and now we have reached a point where we want to educate about what we can do for the power industry. So can you tell us a little bit about how the power industry correlates with the global healthcare industry?
Yeah, thanks, Monica. And thank you all for joining us. I know it's a busy time of the year. Everybody has a lot of priorities, but I really appreciate all of you getting on together here on this show. We want to share some of the things we know and we have come across working with a lot of customers in a variety of industries, and healthcare being very big on our portfolio. As you all know, the global healthcare industry is massive. This is no news, and it's rapidly growing as well. And just as you all know, we're all aware, massive infusion of technology and connectivity is rapidly altering the way the products are designed, qualified, and used. And it's no secret now that what once used to be called as an interference is now necessity. I'm talking about Wi-Fi, Bluetooth, and possibly in the future, other levels of connectivity. So considering how massive the devices industry alone is, it's important that we recognize the evolution and some of the fundamentals that never change, even though robotics and artificial intelligence infusion is rapidly altering the way the products are conceived and evolve. It's definitely some of the fundamentals will never change. The safety aspects, the EMI aspects, emission regulatory aspects, they don't change. They've been around forever. So we want to touch upon some of those things today.
Awesome. So with that, we'll share the agenda for today. So Anil will go over some of the definitions, some of the design qualifications and certifications of the healthcare industry solutions, as well as the power supplies. And we'll go over some of the products and standards for the industry. And then we'll talk about backup power and wrap it up with the application examples. So just remember that for this particular webinar, we will be hosting trivia at the end. So if you want a chance to win a Whoop Super Neat band, please stay to the end. Just a disclaimer, employees and reps are not allowed to win this particular prize, but we encourage you to participate and stick around until the end. And by the way, if anyone doesn't know, or if someone doesn't know what the Whoop is, it's a biometric watch. You kind of wear it on your wrist to when you're working out or even sleeping. You'll just like keep track of some of your biometrics. And with that, I'll pass it over again to Anil, who's going to talk a little bit about the overview of the general requirements for the healthcare industry.
Yeah, thank you. So that's a fine example. You know, a little wearable band has so much capability. It can actually monitor you all the time. And in future, possibly, we'll even start dispensing medications. Hopefully, we don't get there this quick. Some of the fundamentals of power systems engineering, general requirements haven't changed a lot, but it's good to do a refresh. And by no means, this is a tutorial. It's not an educational course. We want to keep it brief because a lot of people who are here are not actually designers. They don't have to actually deal with all the things we talk about here. But frankly, people that require to manage programs and people that are required to do sustaining engineering and buying and selling, alternate parts, etc. They also have to occasionally catch up and find out what these parameters mean. So hopefully, will help to will enhance some of the basic knowledge. So, as you know, fundamental to all medical systems is providing proper functional requirements. Proper voltage, proper power, clean, ripple and noise, and then as well as ability to work all the subsystems at the same time without interfering with each other. Then the safety always dominates all the regulatory compliance. Being healthcare, it's easy to expect plenty of controls around it. I mean, frankly, all of those are look burdensome, but they're all a necessity in the world of engineering. So we'll touch upon some of those aspects as well. And the environmental sustainability part of it has also a substantial impact on how you select materials and what is approved and what's not approved. Particularly the RoHS and REACH, they may be to some degree tied to environmental, but they also impact the supply chain heavily. So we need to be keenly aware of what they mean. And the interface element of it, as we know, is that picture is a very good representation. All of those may be interconnected, and then there's a variety of personnel operating remotely as well. They need to see what's going on. They have the complete ability to interact, and that's all because of the ability to connect each other perfectly. So the ability for the designer is one thing, and then the company that has to make these products have to also comply to some very rigorous quality standards, and to make it all concise and presentable. There's this ISO 13485, which governs a good part of how the operations are, and we can touch upon some of those aspects. And needless to say, medical industry, of course, is a very high investment, and longevity is fundamental to the industry. So everyone expects a high return on investment, which also means high availability with very low maintenance. In other words, very high uptime, very low downtime. And that doesn't happen by accident. We all know that. So there are some aspects to consider, on how to avoid getting into a situation where we have a lot of downtime and needs high maintenance. And time to market is obviously fundamental to everyone. Everyone wants to get to market quickly. It's a very competitive world, but there is some fundamentals in the product development that cannot be compromised. So there is some method to that, rigor as well. We can talk about some of those things. And then clearly, the total cost of ownership is important because a lot of people will be willing to invest heavily, but they really need to see that it's worth investment over time, and the cost of maintenance, cost of owning something, cost of replacing something all play into the equation. So it's fundamental to commercial to have a very high, cost of ownership should be low, and a very high cost of, return on investment.
Yeah, absolutely. And you talked a little bit about the stability and the reliability that is the most important thing for the power. Can you tell us a little bit more about how that functions or the functional requirements?
Yeah. So on the functional part of it, seems like this is where it all begins and looks always the same. You have an input power available, and we have to deliver a bunch of DC voltages for all the subsystems. And there may be some other kinds of voltages. Occasionally, there's a battery backup involved. We need to blend that seamlessly. If something goes wrong, the battery takes over. So many of these are really very basic in conceptually speaking, but when the medical world learning a certain complexity comes in, because you're dealing with patients, you're dealing with human again. So there's also a thing about the operator involved here. So there are some rigorous design procedures here. They're not vastly different from the consumer and the industrial world, but they're certainly more restrictive when it comes to dealing with a patient. So those considerations will come into play heavily in how you build up these blocks. Then obviously the very important part is interference-free, clean, glitch-free power with clean DC voltages and clean AC voltages, no harmonics. So these are definition by definition built into the standard itself. But in any case, we have to address them purely for the reasons of making the system work well. And occasionally there's sequence control because a good part of these systems use normal computing techniques. Lots of regular embedded computers are used here, except they're medical grade. So the requirements of sequencing the different voltages, because there are processes involved, there's mixed signal devices involved. So some of these features are fundamental to designing. Then the emergency features are built into the systems as well. If something goes wrong, you have to have the ability to turn on and turn off or reset, because there are such systems that will need occasionally a friendly reset, or sometimes you have to switch over to something, a backup power. So the ability to control with an on-off locally as well as remotely is fundamental to medical systems. Then you also expect that thermally that the systems are operating in an environment where you may expect high temperature. The whole facility, for example, the hospital and the surgical room may be cool, but because of high density of equipment, the local ambient temperature may be very high, but that factors in to our estimates on what size of power systems you need to be able to power the equipment reliably. And the second part, of course, is we don't need to make the environment worse. So obviously, your system has to be efficient, so you don't add more heat. So those considerations play heavily into defining. The good part of the reliability that we talked about earlier and high availability is to dealing with the subnormal and the abnormal conditions. The grid is never stable, although it appears to be. And there's also the ever-present threat of lightning, ESD, then there's EFT, man-made noises. There's always some amount of motors, elevators going up and down. So all of the things you expect in an industry, they're also available in a medical facility. So some of those interference mechanisms are no different here. But the good news is the standard captures them all. We need to be cognizant of that. And fundamental to all medical system is a high isolation level between hazardous energy and the patient, which is very vulnerable. So defining a proper class of equipment is critical. So we'll talk about some of those and what the standard says and what the requirements are.
Awesome. So I think, Anil, that I can safely say that some of these requirements can apply both to industrial as well as medical. So what really makes this two different industries unique to themselves? And what makes the medical industry so special when it comes to power and reliability?
So as we said before, the real engineers who are dealing with the products and creating them are keenly aware of the differences because they're very focused on a certain product, a certain market, and we don't have to worry about what is not stated. But for the general people, for the other kinds of non-engineering class of people, it's important to know that the human being is the same. You're dealing with one level of knowledge and training in the consumer industrial world, whereas in the patient world, in the medical world, the patient is just unable to respond and more vulnerable to a hazard. So the hazard criteria are very different, and then the product engineering accordingly is different as well. Then the risk to body, life, and property obviously is always the same. You could start a fire, you could get a shock, you could trip over, get injured, and it's more so when there's a patient involved because of the same criteria, all vulnerability and inability to respond. Then normally the normal and fault conditions, whenever there's a fault involved, the operator trained personnel, as you see in the image there, is highly trained technician is going to reach out into this. But in the medical environment, the operator is generally a nurse or a non-technical person, but who's also well trained in dealing with that particular equipment. So we need to keep in mind that the nurse also is vulnerable to a certain amount of risk. Then there is always a potential of an accidental contact in the industrial consumer world. We take it for granted. We have a laptop power, desktop power sitting all over around us. We don't care because it's already designed to be extremely safe. We've never had to worry about getting shocked by a cell phone charger, right? But in
Right.
the medical world, that kind of equipment, as simple as a phone charger, is really should be kept away from a patient contact. Pretty simply speaking, it's way too risky.
Right. Yeah. So, and we also hear about the IEC 6601, which is the regulation for power supplies and medical devices. Can you tell us what really we should focus on? Because I think it's become a keyword in the industry, but what does it mean and what part of it really we should be worried about when it comes to selecting the power for a medical system?
Yeah. So the good news is a good part of the is worrying about what definition, what class of equipment, what class of uh, what do you call as controls applies is all defined in the standard. In the industrial world, the safety standard, EMI standard are all different. They basically the safety standard is mandates a certain requirements, whereas the emissions and immunity, etc., are left to the system designer to determine what is acceptable. There is no regulatory body there. Yes, there are procedures on how to evaluate them and define the acceptance criteria, but in the medical world, it is implicit. The standard tells you clearly for what class of equipment, what level of performance is acceptable. For example, the EMS uses a standard where basic safety and essential performance is required. In addition, the certain procedures can be carried out while in an air transport environment, either aircraft or helicopter. So some additional needs come into, which is called the DO 160 needs come in. But in most of the cases, the middle standard, the dash one, which is a home use standard, it requires most commonly used is a class two power supply, meaning a person who's just can pick up a phone and plug into, rather plug it, take an appliance and plug into a regular wall outlet.
Okay.
Those have to be very portable. So there are certain procedures and certain standards imposed on that. So selecting the proper class is important, and that's what is available at the 60601.
Okay, so to get a little bit more technical, what does it mean, the proper class? What's the distinction between the classes?
Yeah, so very simply speaking, if ever there's a earth available in AC wall outlet, and if the equipment is tied to that earth, you should consider yourself more safe or rather less at risk because you are the patient that can accidentally touch the equipment is not exposed to any hazardous voltage. So the class one automatically will involve a three-prong plug where the middle prong is an earth. So it's one of the most fundamental distinctions and naturally brings up a question. If that is so good and so safe, why even have another class at all without the earth? Isn't that a high risk? Yes, it is no doubt a higher risk, but then the procedures of designing are also different. So there are more rigorous requirements in terms of isolation, insulation, and leakage current, etc. So the most important definition is class one and class two at a high level, and that separates the two equipment in terms of defining, specifying, and qualifying.
All right, so we'll go ahead and move over to the insulation and the isolation of the power supplies. Can you tell us a little bit about the fundamentals there?
Yeah, a lot of information is available. People can read them all, but I wanted to keep it here in a very elementary level. Is the most important parameter for all human safety is the risk of shock. So you want, no matter what happens, you want the person at the other end, receiving end, so-called safe end, and that person should never get a shock. So how do we do that? Is to provide very high levels of safety, meaning if you feel like the primary live circuit, which is the wall power, is a 120 or 230 volt, the insulation system has to be so high that about 20 times of that much, it should be able to withstand forever. So, so most important requirements is whenever you have live circuit from a primary to primary, you don't have to worry so much. It's just an operational requirement and human contact is never there. It's only intended to make sure one circuit works along with another circuit. And whenever there's an earth involved, you have a primary circuit and an earth circuit. And in other words, the circuitry is connected to the earth or sheet metal. Then all we need is one level of insulation. In other words, it's called one MOP. It's called means of patient protection. So that is enough to say that it is insulated. But whenever there is a human involved, in other words, there is a, as you see in the diagram, there's a primary circuit on this end, which is a wall power. And then on the other side is the secondary, which is where the patient can get connected or the operator can get connected as well. There we need two levels of protection or two means of protection. It's also commonly used in the industry as double insulation or reinforced insulation. So the difference between the two, it's kind of, it makes it's very intuitive and makes sense logically speaking, that if one layer of insulation fails, the other one should be sufficient to protect you. But what is not stated here, which is where the engineering considerations come, is when one level of insulation fails, what happens if the other one is also failing, because now it is seeing double the stress. So it's like you're trying to build a column and to hold something, and if that column or a rope fails and the other one also fails, that's not a good design. That's not acceptable for medical systems. So what we talk about here is each of the layers has to be capable of withstanding the level of testing required. So by specifying for 2 MOP a very high level of test, it's kind of a bit confusing to talk about isolation. Usually it means separate the two. Isolation should have been somewhat measured by a distance rather than voltage. But the isolation specified as a voltage means we're going to test that insulation's ability to withstand by applying a voltage. And that voltage will be very high compared to normally used voltage, or where the thing is plugged into the wall. So the concept of creepage and clearance. Clearance simply means you got two circuits, we have to be separating them by a certain distance. If you look at any of these power supplies, the image is shown at the bottom here, there will be clearly a live circuit, a hazardous circuit area, and then a safe circuit area. It doesn't mean that everything is touchable, but there's a clear distinction between the two, and there will be an equivalent of two layers of protection or 2 MOP. So the concept of clearance and creepage is, first thing is to separate the two. The second, where separation is not possible, we can actually cut a notch in the board or an insulator and make it equivalent to a higher level of clearance. In other words, it's called creepage. Then it's basically not a straight line distance, it goes around the bend. So for both of these, there are rules in the design. And so it's important to know that none of these is negotiable for a certain class of equipment, as we've seen before. For class 1, these will be a little lower, but for class 2, because there's a missing earth and the human becomes the earth, the levels of test are much higher. So it should be clear that fundamentally, wherever there's a person involved, this 2 MOP or two means of protection is needed.
So do you think that our Christmas lights, I know everyone's getting ready to put up those Christmas lights, are those have insulation and isolation as well, or
Yeah,
no?
good question. I'll tell you. Whenever you see a person dangling on a ladder on a tree and trying to, mess with them live, it's taking a lot of risk. And certainly those are not welcome in the medical world. But yes, the certain amount of insulation testing has already been done. And the good news is the safety agencies have already looked at it and made in billions and seen that accidental contact is very rare.
Nice.
There's two fuses also in there,
We're all safe.
but don't play with it if you're not qualified.
I won't. All right. So let's go ahead and do like a little summary. Can you tell us the general safety certifications here for medical?
Yeah, some of this we already talked.
Mm-hmm.
So once you define the class 1 or 2, certainly a set of features fall into place automatically. But the open or enclosed also makes a big difference, because whenever you have an open system or a power system, a backup system, inverter, battery, whatever it is, the moment you open something, your hand should not accidentally contact. So there are some procedures there intended on how to protect the operator. Definitely, we don't mean that a consumer or a patient opens something. That's an unintended use. But The equipment classification brings about certain design considerations there. The most fundamental thing is never allow an accidental contact with the hazardous circuit. That's important. Then the bigger classification for the patient, the medical world, is the category called body floating or cardiac floating, depending on how they're used. We have another slide which shows a little bit more illustratively. So yeah, can we go back to that, Monica? Just the previous
Sure.
slide. Yeah. So we talked about the MOOP and MOP. Sorry, a P is missing there. Yeah, so the MOOP and MOP basically means means of operator protection and means of patient protection. So there are still differences because the patient is more vulnerable. Hence, it's natural to expect that the insulation systems, clearance, creepage, as well as leakage, all should be lower because of potential patient contact. But the operator is no less human, so some amount of that rigor applies to the operator as well. Then we talked about creepage and clearance, simply speaking, maintain distance between circuits. Then fusing is supremely important. For example, as we noticed before, in the class 2 world where there is no earth, uh, so there's no distinction between line and neutral. So medical systems require that both are fused because both could be treated as line or live, especially in Europe, because in Europe they really don't consider neutral as earth, it is considered live. So dual fusing is quite common. Then CF needs cardiac floating, especially when they contact the heart, heart tissue or proximity to the heart, becomes very special. So there are some requirements. We will touch upon some of those things. Then fundamental thing to all safety and products, medical products, is that long-term damage of insulation. For example, we start today and it's all brand new and it looks like it passes all the testing, it's more than meets the requirement. But what if it's sitting in a closet for a couple of years and then you see that humidity and a little bit of local pollution has crept into the design, into the product, and have degraded the insulation? I mean, think about it. You provide a certain 2 layers of insulation and something else happens around it and compromises that. So what do we do about it? So the one good news about those effects is the standard even defines what class of equipment, that based on the type of installation, and some of them are pollution degree 3, which means that it's extremely pollutive. It could be even conductive. So there are some special techniques on dealing with it. So we need to be cleanly aware that what is good today has to be good forever, at least from a safety point of view. So the last and not the least one is the implantable devices. So whenever you have life-sustaining devices, the rigor of design is very high because you don't want a failure there. It's about maintaining life. And so the requirements in engineering, manufacturing, quality assurance, and very rigorous record keeping documentation all come into place. For example, in our operations, we have a section there where we manufacture goods that power the artificial heart. It's very tight. I mean, my people are saying that even if you just move a table, you need to document that and tell them why. So those kind of procedures are required for the implantable devices. Then the EMI considerations. So safety considerations are well defined, non-negotiable, and more or less same rigor is the EMI considerations, because the last thing you want is the medical system interfering with each other or causing problems to another equipment within the building. And then worse, not meeting the local regulatory standards, you cannot go to the market. So it's important to know where we stand when it comes to emissions. Then many of the frequency ranges of interest are same as industrial world. In other words, the behavior of goods when it comes to emission, and also immunity. How immune are they while they're working in a dense environment of equipment? Those considerations are also quite common. Then clearly, because of the rigor of medical equipment, class B level, in other words, lower level, there's two A and B. B obviously is the lowest limit, and we need to enforce that, rather the standard enforces us to meet that limit. In other words, it's emitting less, and it's also more immune. Okay.
So we'll go ahead and talk about the different classes. I know I gave everyone a sneak peek, so we'll move over to that now.
Yeah, this is one of the most important classifications. You will see at the top of the list of all medical system specifications is where is the part used? Does the human body float or rather sit on a bed, for example, here with absolutely no electrical contact with anything? That's a reasonably safe environment where you're just being monitored like in a MRI or CT, etc. There's no probes connected to you. You simply lie on a bed and you're not electrically tied. So that's a kind of most benign operating mode. Then there is the body floating is there is some part of the system, a diagnostic tool, is actually connected to the patient body. In other words, the patient is actually in electrical contact with what we consider as a secondary side, the non-hazardous side. But the reason it is non-hazardous is it is by design after recognizing that it is going to be used this way and there is a patient involved that is electrically tied to the circuit. So nothing is accidental. So defining the product BF automatically means I have to contain the leakage current going through the patient body as well as meet the 2 MOF insulation. And CF obviously, is the most rigorous one, where they're in very close proximity to the heart. Whether the surgical procedure or it's simply a monitoring procedure, as long as the electrical circuit is tied directly to the heart tissue or very close to the heart tissue, the leakage current requirements are very low, and they have to be like 1/10 of what is permissible here in the BF category. So that places enormous burden on the design of power systems, especially when you have a lot of subsystems in play, and all of them have the potential to add leakage current into the product. So we need to be very careful about this category.
So I know cosmetic surgery has become pretty popular. What would that be considered in the spectrum?
Yeah, typically cosmetic surgery gets into the BF category because
Okay.
they do invade and sometimes they actually poke holes into the skin. So it's safe to assume that we should design it to the BF category, but definitely not to B.
Interesting. And can you tell us a little bit of how the government regulates some of these devices, specifically maybe the US and
Yeah. So obviously, the American, North American, and European requirements are a little different. In the European system, the voltage is much higher, and they're also structurally different. They use mostly floors that are regular tiles and walls of tiles. Over in the US, we tend to stay with more wood and more insulation all around us. So the criteria are different, both for consumers and the medical world, and also a little more sensitivity to how the systems operate and interfere with each other. So Europeans typically tend to be more regimental about those, but that doesn't mean it's more relaxed here in the U.S. because the FDA actually governs these 3 classes as we discussed before, and these 3 classes basically define, in addition to the other configuration like equipment earth, the BF, CF, B category, there's the FDA classification, which requires certain types of rigor to be built into the design. I mean, it's a little more, this requires a little more detailed assessment. So, but just be aware that FDA is always involved when there are medical products being designed and certified. It's one of the long poles in the tent. And companies that are into this business know very keenly, are keenly aware of how much control is enforced from the FDA.
so as a user, how do I, if I was to buy a power solution, how do I ensure that I know that this power supply actually meets the
Yeah.
expected certifications in the
Yeah.
industry?
Thankfully, people that are buying equipment, generally in the medical world, you don't simply go and buy something directly off the shelf or Amazon. Yeah, certainly if this is categorized and meets the medical requirement, FDA requirements have already been considered in there, and so we don't have to worry. The average user doesn't have to worry about how to ensure compliance. So there is also another simple way to identify what the product requirements are met or not. The label and the top level definition of the product, for example, even as simple as a desktop power supply, medical grade, we clearly state all the requirements it has met, and look at all the markings there. They tell you clearly that there's FCC mark there says we met the EMI considerations. The safety agencies that we listed here have clearly evaluated. There's a whole report that comes with it, and then they're also constantly maintaining those reports and updating them. So the general user gets a lot of information just by looking at the product definition, and if you have the product in hand, the label will tell you a lot more.
Right. And can there be any risks, any faults, or is there any risk there when it comes to the installation itself?
No, you don't have to worry. That's a good news. The moment you have a product that's certified, a good part of your burden is taken away. Somebody has already spent the time and investigated and then certified it. So that's really good news. So
Awesome.
on the one hand, the standard seems like onerous and burdensome, but on the other hand, you wouldn't know what it would be without them.
Right.
Okay, so as we said before, a good part of engineering considerations apply to ensuring proper function, defining the right class, designing in the right protection systems, and providing the right creepage clearance, etc. But like I said, what if something goes wrong? We think that always the mains voltage is clean, and there's no abnormalities from nature. So sometimes you can get hit by a lightning, and then an insulation system can fail. But as we said before, what happens when you have an insulation breakdown? Thankfully, the two-mop is your best insurance against shock, because if one of the thing breaks, the other one, which we just discussed earlier, is equally good enough and will meet the requirements, is there in place, and that's the certification part of achieving two-mop. So we have to be constantly aware that we think that the protective earth is there, which is protective by definition. In other words, it is robust enough that it doesn't break down accidentally or in degrade over time. So, for example, things that can get rusted, the boards can get loosened. Those things don't happen in the medical world because there are different standards on how they are defined and connected. So you have a couple of levels of insurance there against an abnormal thing, and usually the lightning, ESD, temperature effects over time, and time and temperature effects all tend to degrade insulation. But the beauty of the technology we live in is there are materials and components that are supremely robust, and you can pick up a very old device like a radio or a laptop and power it up. Definitely, they're not going to be of any risk just because they're old. So those same considerations apply in the medical world too, with a notch higher in terms of specing and testing. So we can rest assured that if designed properly and meet the requirements of the standard, the normal fault modes are both captured into the certification. For example, there's a thing called leakage current testing, where in the normal mode, everybody expects you to be below 100 microampere for the body floating or the BF type. But when something really goes bad, which is very rare, then the safety agencies do recognize that for that very abnormal situation, a higher level of leakage is allowed, because the belief is if something goes wrong, some action will take place and it will be remedied, or at least there'll be a caution sign that says do not use, and it'll be taken out of service. But certainly the standard agencies deal with it and define it. So the good news is we don't have to speculate on what kind of abnormal situations you have to worry about, because the standard defines it.
Right. So we did get a question from the audience. So if you have multiple isolated power supplies, can you tie the output return to ground via high impedance or other methods so common mode voltage doesn't float up too high?
Okay, whenever you have a fully isolated supply, so-called what we call typically as SELV, meaning safety extra low voltage, and the outputs are completely uncommitted, meaning the return is not earthed, you can feel free to earth it. But I think the functional requirements dominate there. For example, you have two circuits, one receives a 5 volt, the other one receives 12 volt. And if you feel like both of them share a common connection inside, then it's okay to connect the output, the power rails as well. So it's left to the system designer on how you want to connect all the returns together. Generally, there are no issues if the circuits are tied together at one point.
Yeah, and for the person who asked the question, if you want to send Anil an email later, I'll make sure to send his information over. He can absolutely help with that if you need
Thank you.
further assistance. And then Anil, I know isolation is a big keyword in the industry, and now we sell isolation transformers. Can you tell us a little bit about our isolation transformers?
Yes. Thank you. This is a really godsend product. I have to say that, on the one hand, we can say that everybody takes all the precautions. Systems engineers are good at specifying, picking parts. And then as you integrate them all, you got a monitor, you got a display, you got sensors, you got a camera. And let's say you're building one of those complex systems. And then it could even be as simple as a cart. What seems like a simple portable cart actually has multiple subsystems in there, and generally, when you integrate everything, you realize that each item has added some leakage current. And overall, remember, leakage currents add up, straight math. And so if each item has a 50 microamp leakage current, when you put five together, they all suddenly become 250 microamp. And lo and behold, now you can't get this product certified anymore as a BF because that criteria of 100 microamp stands. The good news is if you ever run into this problem, the isolation transformer is a great solution. So this will connect to the mains and give you a safe, isolated, same 120 volts, 1:1, or they could actually make it 230 volt as well. So, and they're very simple devices. They're compact. Yes, they're a little heavy for what they do, but the good news is they're very compact. It looks more or less like that in a toroid with wires coming out, and they can withstand the same 4 kV RMS that is required of 2 MOP. And once this is put in, the requirements on the electronics downstream actually reduces. And in other words, it may or may not need to meet 2 MOP anymore because this one takes it's like putting a really big barrier in the front, and then you don't have to worry about the other barriers. And the good news is, like I said, this transformer actually limits the leakage current because it is structurally such that it doesn't have too much capacitance from in to out, and that is all that is needed to control the leakage current. And there's also they put inside what's called a Faraday shield, and that will be earth. So whatever leakage currents happen, they happen within the hazardous circuit, but won't go to the patient, the other side, the isolated circuit. So there are a lot of benefits here. It's very highly efficient, and for the most part, people like the idea that it has multiple outlets. So this is what we call as an isolation station. If the user doesn't need a real station like this, they could just buy an isolation transformer as a simple part, and this whole thing is certified. You don't have to do any work, just buy it with the proper rating, and they're available in a really wide rating. I mean, make as small as 100 watts VA all the way to 15 kVA. They can handle a wide range of frequencies, so this is good for both North America and Europe. And so we don't have to worry about it. Whatever comes in goes out, frequency in, frequency out. It doesn't do anything to alter it, and has a very high isolation. And obviously, because of the high isolation, it does have the double insulation or the 2 MOP rating we talked about. And by and large, it also limits the electromagnetic stray fields that sometimes can affect your equipment. For example, if you have some sensors that are sensitive to magnetic field, big transformers like these can tend to affect. But these particular designs, because of the toroidal structure, have very low interference with the outside electronics. So lots of benefits here. What seems like a simple one component is actually a very good subsystem. So I would say careful consideration to be given on whether you can use this. So
That's great.
medical certification is guaranteed, so we don't have to do anything. You can buy this part and just drop it in.
Awesome. And then we also offer EMI filters. How does the EMC compliance also play a huge role in the medical field?
Yeah, the interference is common. All electronics have some ability to interfere, and they also have some immunity as well, right? It's inherent to electronic circuits. But as you know, the medical system world is uncompromising. You have to have higher limits, or rather lower emissions, higher tolerance, or higher immunity. So that's no accident. So basically, systems engineers should consider checking the system for very early, during very early stages of development. We typically call it pre-compliance, and we offer some of those services for free to our customers. The idea being, I'd rather know a problem early. We don't want a situation here. This is a real plot from one of the opportunities, one of the customers we know, is after they were all done and they're ready to launch into the market, they realized that somehow something has changed and some things happened, and they upgraded some electronics, and suddenly, lo and behold, there's a noise coming up here. The solutions to this are not easy. They will need time. They'll need time. They need investments. You have to go to a lab and carefully validate it, and then start going backwards and find out what happened and where is the source of noise. And more often than not, uh, the source of the noise is easy to find, but it's very hard to fix. And then one of the biggest problems with EMI resolutions is whenever you need a component that you feel is a good one. Unfortunately, it's bulky. It may generate heat and alter the whole systems engineering from lock, stock, and barrel. So it's a good idea to get a quick sneak peek into the EMI signature, and then not have any big surprises. What you want is to look like the plot on the right, and we're happy to help with something like that.
Absolutely. And then with that, I mean, we've talked about all the certifications, all the safeties. Can you tell us a little bit about our own products and what we offer and what type of applications do our products go into?
Yeah, so this is a very good snapshot. It talks about a variety of systems that are in place. As you know, all of these are very common in the hospital environment. Hopefully, we never have to be under it. But this is just a simple, very small snapshot of what's out there in the industry. Many of you are into different systems that have their own little priorities. But it's important to know that the most basic requirements apply for all of these systems. And we have some good examples. This is a reasonable variety to showcase, but we have some good examples to cover.
All right. So do you want to talk about the examples on this slide?
Yeah, so for example, if you say something like simple like a cart, the cart can be diagnostic, it can be treatment, it can simply be a follow-up routine follow-up after post-surgery. And usually the carts are highly mobile, so they expect to basically have a backup system, rather mobile power system, where they charge it overnight and then have available for all day, so the nurse can go from room to room. So we do have some very advanced backup power systems with the medical friendly battery that is very, very long life. So some of those considerations are already built into the products we make for them. Safety, EMI, I mean, you can just buy them off the shelf and plug and play. However, some of the considerations for total artificial heart or the left ventricle assist devices, they get a little more tricky. It requires careful handling. So we always like to talk to our customers and see what provisions are there. How much are they willing to invest in qualifying and building, or building and qualifying a unique part to them. So the considerations of both engineering and qualification involve substantial time and money. Although because of the nature of the products, we do have some standard portfolio. We're happy to showcase them. We can go up and search on our website and say CF. So this is the most rigorous cardiac floating device we have, and that product you can buy off the shelf.
Yeah.
Then some of the more complicated systems like CT scans and MRIs need a very elaborate discussion. Those are complicated power systems. They cannot be defined by 5 bullets. You really need a very detailed spec document. But the good news is many of them are very fundamental in terms of safety engineering, because all the criteria that are applied to the cart power or the patient monitoring power also apply there. except the scale is big and structurally big. So we're happy to discuss some of those complicated systems as well.
Yeah, and I think we have a pretty versatile team here at Astrodyne, and we're able to leverage our unique standard solutions and provide overall value-added solutions by putting those together. So if you
Yeah,
have any questions on PDUs,
yeah,
feel free to reach out to us, whether through our website or to Anil, and I'm sure that we can put you in contact with the right person to meet all the specifications you require.
yeah. Just to pick up on what I'm sorry, Monica mentioned about PDU. What typically happens is the customers who take on some engineering recognize that they need multiple types of products. It could be a filter going in, and then there's two or three types of different power supplies, and there's a backup involved. I mean, rather than you buy everything in bits and pieces and start integrating them, we're happy to discuss a means of putting them all in one box. We call it PDU for lack of a better term, but think of it as a customized power system.
Well, with that, I appreciate you putting the time on this, Anil, to educate our customers and partners. And I'll move over to the trivia. I know we have about 10 minutes left. So I think it should be enough time for you to take home that Whoop watch.
Thank you all.
So make